Hi, we're Team 2, sharing our final presentation of the analysis and redesign of an RC car. Team 2 consists of members Justin Kim, Shuan Yu, Anuj Raghavan, Sean Colling, Brandon Burlage, and William Hanson. So our project analyzes an RC car, specifically a self-driving RC car. This is meant to be used as a tool to enable access to autonomous driving to students who are hungry to learn about the future. The car uses a Raspberry Pi controller combined with LiDAR and ultrasonic sensors to operate autonomously. RC cars are already very popular and mass-produced, so the self-driving aspect offers a unique twist into the large market. We estimate the annual production volume to be 250,000 units. Our primary customers will be students as well as teachers in STEM-related courses, and secondary customers will be RC car hobbyists and enthusiasts. Here's our FAST diagram, which analyzes the car's functions. The main focus is the autonomous driving aspect, and this is supported by the primary functives. One such functive meant to ensure the product targets primary and secondary consumers through education and entertainment. Another ensures the car is reliable and pleasing to the senses through its visual appearance and sounds. The non-primary supporting functions focus on the performance of the RC car, like movement, turning, and avoiding obstacles. And here we have the function component mapping matrix. All of the functives from the leaves on the FAST diagram shown previously are shown here, as well as the components that are meant to fulfill these functives. Notice that each part is responsible for at least some functive, and there are no functives that use more than 40% of the parts.
After comparing the functions on our FAST diagram with our different customer groups, the core differences lie in the education and entertainment, as well as higher levels of dust and water prevention for outdoor use. This led us to select the wheels, ultrasonic sensor holder, camera holder base, and top battery cover to have alternative designs for product family use. After selecting platforms and modules to narrow in on for redesign and analysis, the team selected the motor holders and camera holder base for manual assembly redesign. The parts were redesigned using Design for Manual Assembly Rules 1 through 3. The motor holders were combined to reduce part count, while screws were removed and snap fits preferred on the camera holder base. In our pre to post DFA analyses, the significant reduction of assembly time for the motor holder and camera holder base and sizable reduction of fasteners allowed us to reduce our overall assembly time from 634 seconds to 501 seconds, increasing our assembly efficiency from about 7% to about 9%.
Looking at the design for automated assembly, the platform subassembly that we selected for the study was the bottom chassis, standoff inner fasteners, and the battery compartment. If we look at the quad chart in the upper right, the high manufacturing cost parts weren't selected because those parts were expensive because of the electrical and sensor components, not the cost to manufacture the plastic and the metal aspects of the part or the assembly. The battery compartment was selected although it was low rating on the quad chart because there was a lot of improvements that we saw for this part, hence we included it for the design. The sensor assembly itself, as part of the build process, wasn't selected for the automated assembly because the geometry of that is very complicated and wasn't fit for automated assembly. Moving on to the next slide where we talk about the design for automated assembly BKMs that we applied to the study. For the bottom chassis, we reduced the part counts and we reduced the fasteners by integrating all of that into the injection mold of the bottom chassis. Therefore, we're eliminating the nut standoffs and the screws. Looking into the battery compartment, we actually increased the symmetry and made it alpha symmetric all three ways by removing notches, removing the curved surface on the rear, and also including a cut on the rear surface of the battery compartment. Looking at the cost benefit of doing this post DFFA analysis, the biggest contributor to this is the reduction of the fasteners, as noted in the previous slide. And also, since we increased symmetry of the battery compartment, we further reduced the cost of design for automated assembly. And therefore, all of this resulted with a 34% improvement. And of course, with the assumption that we made for the study of a desired free rate of 10 parts per minute.
After post-DFA analysis, the part was put through process selection to find the best process for the given material choice. We elected to have the chassis be made from plastic, as nylon is a common material used in the RC industry. Once the process selection was completed, only injection molding and machining were left as available options, and injection molding was chosen due to its high output with large batches. The part was then put through DfM Pro to highlight important areas to improve on when designing for injection molding. DfM Pro only recommended adding drafts on the walls to assist with the removal from the mold. Prior to the design for injection molding redesign, the parts costed $1.78 to make per part. The team took to the recommendations from DfM Pro as well as more design for injection molding rules that the software did not pick out. For example, Rules 1 and 2 were implemented by adding through holes onto the standoffs to both minimize and standardize wall thickness at 3 millimeters. Rule 3 was used as well by drafting all of the outside walls and the shafts, as well as the inside of the large lightweighting features. Rule 4 was looked at by removing all sharp corners and adding corner radiuses. Lastly, the lightweighting holes were added to reduce material cost as well as decrease the weight from 120 grams to about 90 grams. Overall, the final cost per part was $1.05, reducing the cost per part by over 53 cents from the prior state and designed for assembly.
The other component we are looking to improve is the motor holder. First, we have to select the process capable of making the part. As you can see in the chart, only sheet forming was a viable option for making this component. Once the process was selected, we moved on to the design for manufacturing. We analyzed the part using DfM Pro. This showed that the holes and slots did not meet the minimum thickness to distance ratio to the edges of the part. The slots also did not meet the minimum thickness to width ratio. This gave us a path for our redesign. Using DFSM Rule 9 and 7, the motor holder was redesigned. First, the tops and sides of the bent sections were expanded to meet the minimum thickness to edge distance of the part per Rule 7. Minimum corner radius was also added at the bends per Rule 9. The flanges were also removed from the base to decrease material and blanking costs. However, the team was unable to expand the size of the slots due to it being a standard with the type of screw being used. Future considerations would involve decreasing the part thickness to improve on this ratio without making the part itself bigger.
For a type of a service that could be integrated to form a product service system, the RC car could be wirelessly controlled by the user by downloading an app that is integrated with a control box instead of an external remote controller such as a transmitter controller device. Such an integration would require an embedded system through Raspberry Pi to establish the wireless connection to the phone and receive inputs from the user. This app could also educate kids on how LiDAR imaging works by providing a 3D map of what the LiDAR sensor is scanning in real time, with an additional camera to watch the car as it drives. By removing the external remote controller, the environment is positively impacted from the reduction of plastic and electronic parts or waste. To sum things up, through our DFA improvements, we have a 132.91 second reduction for the manual assembly and a 12-cent assembly cost reduction. Our DFM improvements for the bottom chassis was a 73 price reduction and a 4-cent cost reduction for the motor holder. Some critiques for the RC car design is that we could have reduced the part count further to optimize the automated assembly process more, but most notably, a lot of the electrical components were out of scope for this project analysis, so the team kind of felt backed up into a corner of how they were laid out. If we were to start over again, we would have grouped all the electrical components into a single compartment or a sub-assembly to reduce the manual assembly requirements. That being said, thank you for paying attention to our Team 2 RC Car DFM presentation.